Okay, welcome back. So it's my pleasure to introduce Shing-Tung Yau from Harvard, who's going to talk about canonical metrics and stability in mirror symmetry.
Hey, thank you. Well, it's great to give this talk in honor of Professor Kuranishi. Since Kuranishi has been in Columbia in 1961, the subject of geometric analysis is taking off with many important people. Later on, of course, there was Fong, who has trained a lot of very important people who come from Columbia to Harvard, in fact. Since I've been in Harvard for that many years, I have received more than 5 or 6 people, good, outstanding PhD from Columbia who become BP in Harvard. And I must say that I'm very proud and very pleased by their participating in the geometry of analysis in Harvard. So to name a few who I'm working with in the last few years was Adam Jacob and Sebastian Picard and Tristan Collins. And these are really brilliant PhDs who I learned a great deal from them. Although on the surface I led the research, largely they are doing the major work. Especially for Tristan, who has been really doing brilliant work, one of the very best in the subject of geometric analysis. So I'm very pleased that I'm going to talk about this, the work that I'm doing with him and also formally with Adam. So I'm going to talk about this subject now.
Yeah, sorry, could you just move a little bit closer to the microphone? I think.
Yeah. Okay. Can you hear me now? Better?
Much better. Thanks.
Okay, sorry about that. Okay, around 1980s, string theorists observed that Calabi-Yau manifolds come as a pair, which are equivalent from the point of view of quantum field theory for string compactification. And they call it type A and type B. So type B theory is compactified on a Calabi-Yau manifold, which means R3, 1 cross X. Type 2A is compactified X hat, and these two string theory are supposed to be isomorphic. And this isomorphism is extremely interesting because type 2A is supposed to reflecting symplectic theory, symplectic geometry, and type 2B is on complex structures. And so we learned a great deal about complex structure from all the previous works by Kurayira, by Kuranishi, and many other great people. But symplectic geometry was just developing in the last 20 or 30 years, and I think the development of symplectic geometry learned a great deal from complex geometry through this mirror symmetry. And the reason is that mirror symmetry interchanges complex geometry and symplectic geometry, and in some sense they are supposed to be isomorphic to each other. And mirror symmetry attracts a lot of attention in mathematics, especially in algebraic geometry at the beginning, because it tells you how to count rational curves on the quintic. There's a famous work that started by several people. Now, both type 2A and type 2B come from a distinguished set of objects, which is called BPS, or supersymmetric planes in the theories. In type 2A, these distinguished objects are called special Lagrangian cycles. And in type 2B, these objects are holomorphic vector bundles with matrix solving a nonlinear PDE called the deformed Hermitian-Yang-Mills equation, which is a major subject that I'm going to talk about today. But the motivation comes from mirror symmetry, so that's why I want to say something about it. We want to say these two objects are isomorphic in some sense. And in what sense, we need to explain more carefully now. So that was a motivation. Now we come to the subject clearly. Suppose you have a Calabi-Yau manifold, which means you have a complex structure, integrable complex structure, and has a holomorphic volume form and a scalar form. Of course, Calabi-Yau manifold may be you may take a finite cover to have actually a globally defined holomorphic volume form, but let's just pretend it has a holomorphic volume form. The famous work of Harvey and Lawson in 1982 says that there is a submanifold in a Calabi-Yau manifold, which is called Lagrangian if the Kähler form restricted to the submanifold is equal to 0. And it's called special Lagrangian if there is a constant theta hat which satisfies this equation, where capital omega is a holomorphic n form and exponential minus I theta hat, and then the whole thing, take the imaginary part, restrict to L is equal to 0. This is something called Calibrate geometry by Harvey and Lawson. So this was found out much later independently by the physicists. They call it super geometry at one point, but now we all call it special Lagrangian. So in honor of Harvey and Lawson. So these are very beautiful subjects, the submanifold, so we will talk about it now. These special Lagrangian are something called Calibrate submanifolds according to Harvey and Lawson, and they are volume minimizing in their homology class. And this volume minimizing give rise to many beautiful properties of these submanifolds, and Harvey Lawson was trying to look up important examples of minimal submanifold in high codimension. That's how it comes up at the very beginning. Now, a local model for the special Lagrangian equation for this manifold is given in the following way. Suppose you have a potential is a function from Rn to R. Then the gradient map, the graph of the gradient defines a Lagrangian submanifold in general. So R2n is isomorphic to Cn, and the graph is the Lagrangian cycle. Now we call it special Lagrangian by rewriting the equation here. Rewriting the equation special Lagrangian imaginary exponential minus I theta capital omega. We rewrite this one in this setting. It turns out to be equivalent to this equation, which is written down by Harvey Lawson. So arctangent of lambda I of the Hessian, lambda I of d square f is a Hessian of the function. It's a real value function, so you can talk about Hessian. And then you take arctangent and sum it up together. This would be a constant. This is equivalent to the equation that we just saw. So this is a local model. So writing the submanifold in a local model, you can write the equation in that way. This model is very important because this motivates our writing of the deformed Hermitian-Yang-Mills. Now this is a fully nonlinear elliptic partial differential equation for the potential F, and this is an interesting equation, not easy to solve. Now Richard Thomas, about 20 years ago, maybe 22 years ago, and I worked together when he came to Harvard as my postdoc. We conjectured the existence of special Lagrangian in a given homology class in the Calabi-Yau manifold. It should be related to some kind of algebraic geometric notion of stability. We wrote down some conjectures in about 22 years ago, and the conjecture is still unsolved and is still very interesting, I think, the existence of special Lagrangian in a given homology class. Now, roughly speaking, Miller symmetry predicts that special Lagrangians are Miller to holomorphic vector bundles with Hermitian-Yang-Mills connection in a large volume limit. So the existence of Hermitian-Yang-Mills connection was proved to be equivalent to slope stability of the bundle according to the work of Donaldson in 2 dimensions, Ken Ruenberg and myself in high dimension. And this was not an easy theorem, but anyway, we know they're equivalent to some algebraic conditions. So some existence for nonlinear elliptic system is equivalent to algebraic geometric condition of stability. So this is very good, and we hope that the same thing would be true for special Lagrangian cycles. Now let's looking at the Miller part of the model. the special Lagrangian appears in the A model, and you look at the B model part, which have distinguished objects, holomorph vector bundles, with a metric which will solve the deformed Hermitian-Yang-Mills equation. So I'm not sure this is the best name for it, because it's very close to Hermitian-Yang-Mills, but not exactly, so you deform it. And in some sense, it's a deformed Hermitian-Yang-Mills, but anyway, we stick with this name. So, so what's the equation that we are talking? Suppose a holomorph vector bundle with Hermitian metric. Let Fa denote the curvature of the chain connection associated to this bundle. Then the deformed Hermitian-Yang-Mills equation turns out to be equivalent to this statement. So imaginary part of exponential minus I theta hat times the omega is the Kähler form. Kähler form tensor with the identity matrix acting on E, minus Fh is a curvature. Curvature is a two form and the modulus of H. The whole thing power n, and we take imaginary part equals 0. So we have a topological constant Ei minus I theta there. The imaginary part of the equation or the whole bracket equals 0. The real part is positive. So this is a deformed Hermitian-Yang-Mills equation. So why would you come up with this equation? Actually, this comes up, well, first of all, this fully nonlinear system. If you take, replace omega by T omega in here, you replace omega by T omega, means you change the polarization, so to speak, and then let T go to infinity. After some rescaling, it turns out you get down to omega n minus 1 wedge F equal to times omega to the power n. This, of course, is exactly the Hermitian-Yang-Mills equation that we studied 30, 40 years ago. So that's one of the reasons why we call deformed Hermitian-Yang-Mills. When we change scale, the Kähler form, to let it go to a large volume, then it becomes this equation. So, well, it's expected that the deformed Hermitian-Yang-Mills equation, the equation we just wrote down, can be defined for a complex vector bundle up to quasi-isomorphism, so that it defines the notion of canonical matrix on an object in the derived category of the manifold X. Well, for the gauge group, or for the vector bundle becomes a line bundle, this was derived in the physics literature by 4 people here, and I learned it from Andy Strominger, who is my colleague, and Greg Wall, of course, a good friend, and we learned this thing from them. They derived it from a supersymmetric consideration, not from geometry. Then Conan Leung, my former student and my former postdoc, Sasso. So we looked at the SYC construction and found that the solution of the deformed Hermitian-Yang-Mills equation are actually equivalent to special Lagrangian section of the Miller SYC fibration using semi-flat Miller symmetry. So therefore, it's very well motivated from the SYC fibration of Miller, which explains how Miller symmetry looks like in geometric category. So special Lagrangian section becomes a deformed Hermitian-Yang-Mills equation in a very clear manner using the Miller symmetry construction of SYC. So based on the works of DUI here and also Douglas and Bridgeland, the folklore conjecture concerning the solvability of deformed Hermitian-Yang-Mills equation is the following conjecture. Well, at the beginning, not too many people look at it. Now it's folklore. So let E be a holomorph vector bundle. Then we claim that E is a metric solving the deformed Hermitian-Yang-Mills equation, namely the equation I wrote down earlier, Ei theta, etc. Even only if E is stable with respect to some kind of Bridgeland stability condition on the derived category with the central charge defined in this way. Now, of course, Bridgeland stability and all this needs to be explained because it is not even known to exist in a very general case for when the dimension of the manifold is bigger than or equal to 3. So there are some conjecture involving in the conjecture itself. So, but that's fine. At least we have a guideline and a motivation of how to proceed. So that's how the situation goes. Now here I'm going to discuss the progress made on this conjecture when the vector bundle becomes a line bundle. And I think this is very fascinating nonlinear partial differential equation that deserve to be studied much more carefully. So let's see what we are talking about in the case of line bundle. Now it's easier, we don't have vector bundle, so we are looking at a first chain class of the line bundle, which we denote by alpha. But now, writing in this form, we don't actually need to make the class to be integral class. It makes sense even for the alpha to be a H11 with real coefficient, so not necessarily integral class. In the case of line bundle, it will be integral class. So we assume we look at the deformed Hermitian-Yang-Mills equation, omega plus I alpha to the power n. Well, if the equation holds, then we know that by integrating it, it is equal to some real number to the power I theta hat, where theta hat is a constant. This will be a condition for the existence of the deformed Hermitian-Yang-Mills equation. So we assume, therefore, this has to be true. This clearly will be a necessary condition that integral of omega plus I alpha to the power n is in the R to the I theta hat. Now, of course, it can happen that integral is equal to 0 in dimension higher than 3, bigger than or equal to 3, and this will be the obstruction of the existence of solution to deformed Hermitian-Yang-Mills equation. And this is obstruction because this is a topological condition. Omega is a Kähler class, and alpha is a cohomology class. This defines a condition for the omega and alpha, so that it would not exist. But besides that, we'd like to know what else could that be in order for it to be obstructed. So let's write down the equation precisely. The alpha condition, we can write it down to be, you fix a background alpha, and you write alpha phi to be alpha plus dd bar phi. So the change of alpha in a form, in 1-1 form level, is just defined by alpha phi. Then the equation we are looking at becomes this equation, which we wrote down earlier. Imaginary exponential minus I theta hat times this integral is equal to, this form is equal to 0. Now for line bundles, we can rewrite the deformed Hermitian-Yang-Mills equation in this way. This is actually very good because it's exact analog to the special Lagrangian equation, where lambda I will be the matrix, the endomorphism defined by the 1-1 form alpha phi and omega inverse. Omega is the Kähler form. So this is the equation that we are trying to solve now. And theta would be a constant, and theta would be equal to the original constant theta hat mod 2 pi. So original theta hat is defined only as in circle. But given this a PDE, we actually find a lifting of the theta hat to R. Originally it was defined as S1, but the deformed Hermitian-Yang-Mills give rise to a canonical leaf. Now this is elliptic PDE, and by solving the maximum principle, by using the strong maximum principle, we know that. So now we are interested in understanding this equation, which I think is a beautiful equation. The basic observation already give non-trivial algebraic information. The integral cannot be 0, as we said earlier. And now, in order to understand this equation, we want to look at this space. This is the space that we are interested in. So given phi, a smooth function on X, and we look at alpha phi, which was defined by alpha plus IDD bar phi. And then we know how to define this theta omega. So theta omega is simply the equation here. Theta omega alpha phi is defined with summation arctangent lambda I. So given a smooth function phi, we know what capital theta omega alpha phi means. And we look at those phi so that the capital theta minus some theta in absolute value is less than pi over 2. So it's not far from theta, who is the element in minus n pi over 2 to n pi over 2 in that interval, where theta is equal to theta hat mod 2 pi. So theta hat was given to you, but as an element in the circle. So it's only well defined up to 2 pi. And now we look at all the possibility, theta equal to theta hat. Okay, so this defines a space, and there's a disjoint union of n seeds dependent on theta. Theta range from n of them. So now, a solution to deformed Hermitian-Yang-Mills will be a point of H. And by the maximum principle, there will be at most one seed that can be non-empty. And from now on, we shall assume H is non-empty. If it's empty, there will be no solution, of course. And we will denote by theta hat to be leaf so that H theta hat is non-empty. So this will be the notation that we will be using. So now is the analytic data that were given, but we shall discuss later how we recover the leaf theta hat and the non-emptiness of H theta hat algebraically. So basically, we are still trying to do similar thing as Hermitian-Yang-Mills equation, namely the correspondency between deformed Hermitian-Yang-Mills connection, existence of it, to something which is algebraic geometric. That's what our goal is. Now, as I said, it's a privilege that I have two great brilliant young mathematicians coming from Columbia. Tristan Collin and Adam Jacobs has been working with us, with me together. We give necessary sufficient analytic conditions for existing solutions. So this is what we proved a few years ago, maybe 6 years ago. So suppose theta hat is bigger than n minus 2 pi over 2, then there exists a solution to deformed Hermitian-Yang-Mills if and only if there is a chi in that class, homology class, such that the summation here, lambda I are the remember lambda I are the eigenvalues that we define there, and should satisfy this inequality. So so number A and then number B is the total sum that we define there is bigger than n minus 2 over pi over 2. So these are the two conditions we wrote down that we know is a necessary and sufficient condition for the solution of deformed Hermitian-Yang-Mills condition. And we thought already at that point that A should imply B when theta hat is bigger than n minus 2 plus 2 over n pi over 2. And this was removed by people like Lin, who did a good job when dimension equals 3. I think also in 4 too. And now, the important goal for us is actually after this work, which is non-trivial, we want to replace the analytic condition by algebraic geometric conditions. So, so Tristan and I developed the infinite dimensional GIT picture in order to understand this. So this picture was, of course, motivated by many people, including Calabi, including Simon Donaldson, and many other important preceding Greek men. And this space H can be made into an infinite dimensional Riemannian manifold. And so what would that be? Well, we define H is, and then we look at the tangent space of H, this infinite dimensional manifold. The tangent space clearly just smooth functions we can take. And we define a pairing on the tangent space, which is defined by integral of psi 1 times psi 2, the real part of the whole thing here. The real part is supposed to be positive, so this is a well-defined pairing. And this definition is motivated by previous work by Solomon in sympathetic geometry, but in fact, I think it went back to Simon Donaldson and several other people. From now on, we assume that theta hat is bigger than n minus 1 pi over 2. And now associated to this metric, this Riemannian structure, is the notion of geodesic in this space. So we look at, on this infinite dimensional space, we can define one form. The one form is defined with delta I here. And so one form means that when you work on a tangent vector, you give some number. So psi is a tangent vector at this point, and you define it in this way. So this is a one form. Actually, this appears in my proof, the Calabi conjecture, this kind of notation. And this one form integrates to a well-defined function on H with the property that it has a critical point exactly at the solution of deformed Hermitian-Yang-Mills. So a point in H will be a solution of deformed Hermitian-Yang-Mills. There will be a critical point for this functional. And also, this functional will be convex along the smooth geodesic in H. So this very good. This functional, it will be convex along geodesic, and also it will be critical point exactly at those solutions of deformed Hermitian-Yang-Mills. So this gives rise to a way to interpret and understand what these algebraic properties of the deformed Hermitian-Yang-Mills means. But there's a problem. We have to establish the geodesics in order for it to be interesting. Now, so let's understand the following picture. So the functional, in order to have a critical point, we would like to see this picture. So the functional is defined H, and you would like to see a minimum like this, a deformed Hermitian-Yang-Mills. But how do we get that? Well, you see, you may happen that the functional will go down like this, and then you will be not found the critical point. If this critical point does not exist, that means the existence of deformed Hermitian-Yang-Mills is in problem. So the important feature is the slope of this functional near the infinity boundary of H. If the boundary of H, the slope is good, like the green line, so that it will force you to have a minimum, that would be great. So this will lead to so based on this, we would like to see some kind of GIT appear, but except in infinite dimensional space. So in order to connect this picture with the Foucault conjecture that we mentioned, we require 3 steps. So the first important thing is to establish the existence of sufficient regular geodesic in the space H. If it's not regular enough, most of this argument could not work. So we need some existence. And then we need to make sense of some points at infinity, boundary H, and try to connect it with the ideas in algebraic geometry so that we can talk about algebraic geometric objects. And then we want to produce geodesic going to infinity and evaluate the limit slope of I in terms of algebraic invariance. This trying to force the slope is good enough so it will appear as a minimum. So that's the idea of trying to prove existence. Well, so the geodesic equation has been important for this, and in the Taylor metric, Taylor-Einstein metric before, it was considered by several people in Taylor geometry. So what do? We look at the manifold, the Calabi manifold, crossed with the annulus T between 1 and E minus 1. And you got this picture. And then we take a complex Hessian on the total space, and we look at the complex Hessian on X. So the important lemma is the following thing. Suppose we have 2 points in H in our manifold, infinite dimensional manifold phi 0 and phi 1. We want to find a geodesic segment joining phi naught to phi 1 is equivalent to the following function phi on the total space we mentioned up there, which is S1 invariant, circle invariant. That means t is written as absolute value of t. And solving the equation 1.1 as satisfy the real part of it is strictly positive, where at the point 1 is equal to phi naught, and at point e minus 1 equal to phi 1. So this will be, turns out to be a geodesic joining these 2 points, phi naught and phi 1. And that is important for us. Now this is a nice equation, but it is degenerate. Fully nonlinear degenerate elliptic equation. So existence of viscosity solution with any better than L infinity regularity is not guaranteed because it's degenerate. And so this takes a great deal of work, largely due to Tristan. So for theta hat bigger than n minus 1 pi over 2, then for any two solutions, phi naught to phi 1, there exists a C1 alpha solution of this equation, geodesic equation, with boundary data phi naught and phi naught. And the function node that we just declare can be defined and is convex along this geodesic. So this is a fundamental freedom for the whole discussion we are talking. Given any two functions in the infinite dimensional space, we have a solution which is C1 alpha. Alpha is positive, and it's important. We need alpha. And for the geodesic equation with the boundary data correctly, and also I is convex along this phi. This takes a huge amount of work to do. Well, turns out later Drew, Collins, and Lee find out it can be improved, the regularity of this geodesic, improved from C1 alpha to C1 1. So that's beautiful. And H can be complete to be category 0 or negative curve metric space. In this case, therefore, H has a reasonable intrinsically defined infinity. Now, well, so we need to understand infinity of H, the infinite dimensional Riemann manifold. So we call it boundary H, and we construct curves in this H, which will go to infinity. But in doing that, we fix a filtration of OX, the structure sheaf of the Calabi-Yau manifold, with a filtration of coherent ideal sheaves on X. So, for example, the ideal sheaf of some subvariety, etc. Associated to this data, this flat, we have a ideal, is direct sum of this ideal sheaf times t to the power L. So t is a formal variable sitting in Ct. So we get this guy. And we show that this flat ideal gives rise to a curve, phi t, associated to this ideal. We have can write down some functions, and we can then produce the elements in H, which we call phi t. So that as t goes to infinity, this phi will go to the boundary of the infinity, boundary H, so going to infinity. So this constructs a huge number of elements representing infinity. Now this is a curve that you can see in this picture, the green curve. From this curve, we can construct geodesics in H going to boundary H. So by simply joining them by segments, and then we take limit. So this is a way that we can associate geodesics and the functional we had before restrict to this geodesic, and try to understand how it goes to boundary H. So the limit slope of this functional can be computed by hand after passing to a log resolution of singularity of the flat ideal. So this is interesting. So in order to compare this, what we do here with the Bridgeland stability, let's assume alpha to be the first train class of the line bundle L. Using convexity of our functional, we can produce algebraic geometric abstraction to existent solutions to the deformed Hermitian-Yang-Mills condition. So let's just consider a special case. So let's consider a simple case when it's defined by ideal sieve of a subvariety V, and you just look like that. And then we look at the central charge defined in the following way. So the central charge related to a subvariety V is defined to be exponential minus I omega Chern character of L, and so is the central charge defined over the total space X. So we look at the limit. So we found out that if L admits a solution of the deformed Hermitian-Yang-Mills with theta hat that we have in that equation, we must have imaginary of the central charge on V bigger than 0 and imaginary of the ratio between V and X to be strictly positive. So this produces a necessary condition for the existence of the deformed Hermitian-Yang-Mills condition. Now, so in particular, if the imaginary part of the central charge is less than or equal to 0, then X is actually empty. So therefore, there's no deformed Hermitian-Yang-Mills solution at all. Well, you can see this picture better. So this is a case where the condition that we saw, namely this condition, these two conditions, imagine CVL bigger than 0 and imagine the ratio is positive, amounts to this condition. So this will be a case where the solution exists. And then this will be a case when it is violated. The imaginary part of the ratio is not positive. And then this will be the case where X is empty. So these are the three cases that we just mentioned there. So these three cases are important and they are interesting. So this inequality involving these two central charges for all subvariety V are sufficient to guarantee the existence of a solution when theta hat is bigger than n minus 2 pi over 2. That was the conjecture that we make. And this, I think, is very interesting and important conjecture. We also have some Chern number inequality, which we mentioned. So when we finished it, I was rather happy to show it to many friends. In about 5 years ago, Chen, ex-Chen, Shou-Hyung, come from Stony Brook with his student. He wanted to change to a different subject, although he actually still working on it. Asked me to suggest a new direction. So I suggest him to work on this problem, and then it happened to be good work. So many people start to work on this problem too, besides a small group of us in Harvard. So so we want to prove there exists the inequality involving that for all V plus there are sufficient guarantee existence solution when theta hat is bigger than n minus 1 pi over 2. This was true, proved in dimension 2. This is a sufficient condition. And also true for small radius limit, which we can explain, but we don't have time here. And when L is ample, and this is true for several cases and proved by several people mentioned here, as I said, Chen and his students, and some of them come, some people else. And also true for the case when X is projective, and a slightly weaker version can be proved in general. So these are the very good results due to all these people I mentioned here. So the work in number 3 here address a weaker conjecture which does not include the Chern number inequality or the condition imagine CVL strictly positive. Instead, they require some mild analytic point input, but hold in the larger phase angle. Now, let's try to compare our notion here with the famous Bridgeland stability condition. So for the derived category. So first of all, Bridgeland stability needs a central charge. For Miller symmetry, one proposes a central charge which we call Douglas Bridgeland central charge, because Douglas actually was involved in this before Blitzman. So given a element in the derived category, we define a central charge to be this integral, similar to what we wrote down earlier. So Chen E is a character, so works out well for derived category. A Blitzman stability condition on the derived category is very roughly a lift the angle of this central charge to R for enough objects in the derived category. So this assignment to E in the derived category a phase, so that this central charge belongs to positive number times EI phi E, so a well-defined phase number. And an object A in the derived category will satisfy phi A belongs to CO to pi is Blitzman stability if for any object B with phi B there, so that with A morphism to B, we have phi B bigger than phi A. So that is the picture that Blitzman stability would say. So the central charge would look like this in the picture when it's stable. So, well, when it's unstable, it will look like this picture. So flip around. So that's a opposite picture. So the obstruction we obtained by our Verizon framework could be regarded as rising from the surjections from a line bundle to L tensor O of V, where V is a subvariety, O is a skyscraper sheaf support on V. So this is the picture analog to what Blitzman stability says. But on the other hand, the Blitzman stability L tensor OV is not equal to the central charge that we define here. That makes some problem, of course. So, so Blitzman stability conditions are known to exist in dimension 2. We can compare its existence of deformed Hermitian-Yang-Mills using the result of Ackler and Miles. And so this is a work given by Tristan and Yun Xi. They look at the blowing up of P2. You take P2, blow a point. You take L to be a line bundle over this blowing up space. They observe that if L is a solution of the deformed Hermitian-Yang-Mills, then L is Blitzman stable. So that's good. So deformed Hermitian-Yang-Mills implies the Blitzman stable. However, the converse is not quite true. They are Kähler class omega and the line bundle L, so the L is Blitzman stable, but is obstructed from emitting a solution of the deformed Hermitian-Yang-Mills equation. So therefore, we has not solved the equivalence condition, which means that the notion of stability needs to be defined. Either the condition for deformed Hermitian-Yang-Mills notation should be defined, or the Blitzman stability has to be defined in order for it to be equivalent. But personally, I like equation better. So I would prefer to see how to find the right condition for existence of deformed Hermitian-Yang-Mills equation. So we are doing some more works with several people together and not finished completely. Now, strictly speaking, to make our condition completely algebraic, we need to determine the constant theta hat that appears very early on the right-hand side of the deformed Hermitian-Yang-Mills equation algebraically. So we need to understand that theta hat. So we propose to do this by the following construction. For each subvariety V, algebraic subvariety V, we consider the path which is obtained by change the polarization omega. So replace omega by T omega, and when T runs from plus infinity far away, when it's basically a large radius, going to 1, and see what happens. And well, we define the theta hat V L to be the widening angle of this curve, provided this curve does not pass through the origin. If it passes through the origin, we cannot define widening angle. But if it does not pass through the origin, we can do it. And when V is equal to X, when the subvariety is a total space, we expect this widening angle computes the least target angle for deformed Hermitian-Yang-Mills. So this would be a good thing to do. And this is, of course, more topological if we know that is true. And the widening angle turns out to be always defined in dimension 1 and dimension 2. Dimension 2 based on the Hodge index theorem. Not always defined in dimension bigger than or equal to 3 though, since gamma T2, the curve that we define in the dimension bigger than or equal to 3 can pass through the origin. So that means it's not well defined in that case. This example occurs in the case of blowing up a pond in P3. So with Dan C, who is now in Tsinghua, we observe the following thing, assuming dimension, in the case of 3 dimension, if L, the deformed Hermitian-Yang-Mills equation exists with theta hat L belongs to pi over 2 to 3 pi over 2, then gamma T does not pass through the origin, and we have the following Chern number inequality, which is a very nice inequality involve high Chern number. So, we can generalize this to high dimension, one needs to prove it, but so for high dimension will be n minus inequality in dimension n involving Chern 1, Chern 2 up to Chern n. We can now completely algebraize the implication of existence of deformed Hermitian-Yang-Mills in the following way. If dimension equal to 3, and if L admits a solution for deformed Hermitian-Yang-Mills with theta hat bigger than pi, then the Chern number inequality mentioned above should hold, and also theta hat will be equal to the given theta hat. And also for any analytic subvariety, imaginary part of the central charge restricted to V is strictly positive. And now suppose I define for any subvariety, we define a slicing angle by this formula that I wrote down here. And then we want to say that then the slicing angle is bigger for subvariety, strictly bigger. This would be a inequality. So this is necessary condition for the existence of deformed Hermitian-Yang-Mills condition in dimension 3. So we like to say that these obstructions are sufficient also. So these are necessary conditions for the Chern number inequality holds, and also for this stability defined in the following way, in our way, works. So we would like to say that this is necessary and sufficient. Before doing that, actually, I should say that this already is rather interesting for many questions in algebraic geometry, because existence of solution deformed Hermitian-Yang-Mills condition can be found by brute force geometric reasoning sometimes. For example, if you have a homogeneous manifold like abelian variety, or say similar variety is covered by some homogeneous domain, we can solve the deformed Hermitian-Yang-Mills on the domain, and since it is invariant under group action, it will descend down to a solution downstairs. So we can actually solve such a deformed Hermitian-Yang-Mills by simple analysis. And then it is non-trivial to know that all this inequality actually holds, which is, I think, is not clear at all for abelian variety or for similar variety, that this would hold. Now, little is beyond, known is beyond the case of line bundle when with large phase due to serious analytic difficulty. And recently, Jacob showed that in an important class of manifold, which is obtained by projected by OPN plus OR plus 1 here, the conjecture is true even without assuming the condition, the large phase condition. Provide one X a bound which is defined here. Previously, we only has a left-hand side bound. He make some condition that on the right-hand side it also has an inequality. Well, the upper bound turns out to be trivial in the large phase case. The upper bound is natural and should be related to some distinguished triangles in the derived category. We hope to understand this better. Whether how it works in general would be quite interesting. For higher rank bundle, it's not even clear the equation is elliptic in general. Although we can write down the equation, which we did, the question is that whether this is an elliptic system or not. We do not know how to prove that. Maybe in suitable gauge, we don't know. But anyway, this was, on the other hand, solution has been constructed by perturbation near the large volume limit by these three authors. So something should be workable in high rank, but very little is known about that. Well, so our work shows that the notion of stability in the conjecture that I make in the very early pages should be refined. And the obstruction we found have the same general structure as a Bridgeland stability condition, similar to that, but not recovered by Bridgeland stability, which means that we need to refine the condition much better. And also, it's not clear for the correct definition of the Harder-Narasimhan filtration for bundles, whether it admits a solution of deformed Hermitian-Yang-Mills or not. So we know in the Hermitian-Yang-Mills case, we do have a Harder-Narasimhan filtration. It's not clear here. And this is probably very much related to the defined notion of stability for deformed Hermitian-Yang-Mills, which I think is fascinating to look at in more detail. It's possible that understanding the blow-up behavior of the line bundle, mean curvature flow, which was introduced many years ago by Jacob and myself, or other deformed Hermitian-Yang-Mills flow, which was introduced by several people, including Fu and several other people. We would hope that you will give some light on this question. For high-rank bundle, we expect that there can be obstruction related to torsion sheaves, support, and subvarieties. It would be nice to find some examples of these obstructions, and I hope this will be a good account on what we have been doing. And the paper that Tristan and I wrote appear already in Annals of PDE, so last year. Although it was written long ago, but it appears in